We have 80. And then 20. This way. And then here, just like that case, yes, here it is. 20, and this will be positive direction x. Now you could take the other direction positive, and if you do that, your entire diagram will be flipped upside down. But we're talking about the maximum. We're talking, this is talking about absolute value, right? So it doesn't really matter if you take this direction positive or the other one. So here, I do the same thing, summation of moment about x, so you get negative 80 plus 20 plus p of x is equal to 0. Then t becomes positive 60 Newton meter. So if you want to draw that, then you go a little bit down, and here is 60 positive. Now finally, I go from B to A. You could find the wall moment and the stuff from the other side. You get the same result as long as your x positive is here. You get exactly the same curve. Okay? So for the last one, I get my last free body diagram would be $18, 20, and then you're going to have another 30 here, 30. So 18, 20, another 30 here, and then finally you have T at x. That's your FBD. Then if you write this solution, you get negative 80 plus 20, negative 30 plus T at x is equal to 0. So this is going to be a negative 80 plus 20, negative 60, negative 30, negative 90. Take it to the right, positive 90. So T and x is positive 90 Newton. That means that from here to here, you get positive. So that's your curve. Now you have the torque moment distribution. Just like we had axial moment diagram. Just like we had bending moment diagram. Exactly similar to shear moment diagram. It's a function of x. When you have this kind of different loading, it's going to be a function of x. So now, this equation tells me at any x, this equation is valid. Now if this is the maximum, the top should be maximum, the bottom should be minimum. Okay? So T is maximum. What should I do for T? 90. So the maximum shear, in fact, happens a region here, from here to here, near the wall. Sometimes this is according to our expectation. When near the wall, you have the max because the wall is holding up this object, right? But sometimes it doesn't happen near the wall. It's not intuitive. Sometimes it may happen here. So you have to draw that curve. Right? You have to draw that curve. So I'll go ahead and substitute into that tau max, maximum shear stress is equal to 90. What's the dimension of that? Newton meter already. You don't need to convert to millimeter already, but that's already Newton meter. divided by J. J is equal to pi over 2, the outer radius to the fourth power. What's the outer radius? It's 35, right? And it's already in millimeters. So you say 35, 10 to negative 3 to the 4.
That was the diameter.
Is that the diameter?
Yeah.
The diameter, yeah. A lot of people do. You want point? Good. Thank you. See that? It's extremely, I can see that. Well, to be honest with you, I was going to make the same mistake. I thought it was radius. And now I saw Greg was doing the writing and I told him, well, check that number because I thought it was the radius. It's extremely easy to mess up here. Even if you are very good at math, you will make a mistake. No way. That's the reason I say when you go home, practice. So, 35 divided by 2. Okay? What else do I need? Subtract it by 25. 25. Don't forget this 2. Then to negative 3. To the 4. I'm missing something. What am I missing? I put T, I divided by J, and then I have to multiply it by the radius. What should I put for the radius? The maximum possible point. So I multiply that by the radius, which is 35. Do not forget this 2. Then to negative 3. Put it in the calculator. So the moral from this quiz is please read the question several times. You see, we always have extra time, and I see, like I say, the exam has 45 minutes. And then I see after 10 minutes, there are some students getting in. And I say, well, you have 20 minutes at least to double check your result. And what's the part of double checking? The most important part is read the question again. See? Several times read the question. So put it in calculator. Divided by So I got 14. Did you get different 14? No? 14, yeah. I got so mass is equal to 14.4 MPa. If I did the calculate, put it right in the calculator, double check that please. So that's what you get for Tomax. So what's the location Tomax is happening? Is it a particular only one point? Is it the line?
It's happening between A and B.
The entire surface, right? It's not, sometimes it happens only at one particular point. We call it a stress concentration point. Sometimes it happens along the line. What here happens along this surface, from here to here. All the outer radius. You see that? So now, if you have access to this CAD modeling software, you can create that model, put it in the CAD, apply this torque on the loading, and run the simulation. And you see, when it runs the simulation, when you run the contours, the stress contours, You see here is red. The surface here. That means we have maximum shear stress. If you draw the shear stress distribution, and then the maximum is it going to be 14.4 when you look at the result? Yes or no? Is it higher than or lower than that?
Higher.
Why is higher? Why is higher than that? Because the rapid area change here, stress concentration. So this value was the assumption that you have infinitely long bar, that everything is uniform. But near the wall, you have a lot of jump in your stress because of the area change. Okay? So now I want to talk about the angle of crease or deformation. What do we need to do deformation analysis? Why do we do deformation analysis? We had last class. For extra equation we get to find to make indeterminate system determinate. That's the purpose of deformation analysis. Now here deformation we call, in the torsion we call deformation angle of crease. That is how much your bar is going to deform. Alright, so let's draw the bar like that. And it speaks to the wall. And we apply the torque here. So as a result, what happens here? Any point here, and you have point torque like that, is going to deform like that. You see that? The farther from the base, because this point, they're not going to rotate, they're not going to move, they're fixed to the walls. Just like the axial load, when we have two balls, you remember the example we had? There were two balls blocking the object. So there was no room for the object to go from left to right. So this point is not going to move. But when I go a little bit to the right, I have more angle of deformation. Now my objective is to find this theta. That's what I'm trying to do. Okay? So I make a little bit of, instead of considering the outer radius, I consider a point here. Let me draw it a little bit bigger. This is the small, a little bit bigger. So I take a point at location R, and then I have the same thing. See, at any slice here. So let's say from here to here is R, and from here to here is capital R. And this is solid. Let's say this is solid. Now my objective is to find this theta, this angle theta right here. This is different color, green. My objective is to find this angle theta. Right? So this angle from here to here, this arc length, let's call this ES, or just S, the arc length. Another color, let's call that S. arc length from here to here. And then let's call this three-dimensional angle from here to here phi. Okay? And let's say the length of this part that we consider is L. And from here to here, the length of the displacement, we only have a uniform torque. So torque is not going to change. Torque is T, uniform. Now, if I go back to the definition of Hooke's law, what is the shear stress at this point? At point R. The shear stress according to the Hooke law at any point is equal to G times the angular deformation, gamma. And that gamma was the angle. You remember we had object that we have a shear stress, shear load, right, like this, and this object was, twisting to the right. That angle was gamma, right? So here, what is the angle? That is this object. You see, if you don't have torque, this object is going to back. So the angle is phi here, right? So you say d times phi. But just applying the Hooke's law for torsion, not for the axial load. Hooke's law was normal stress is equal to E times epsilon. And this epsilon was not angle, was actual relative deformation, right? Now in the Hooke's law for torsion, this is not normal. This is shear like that, and then this is G times, this is the angular strength, gamma. They are very similar, but not exactly the same. And this number is also different. It is different from G, right? So far I have derived this relation. Now what can I say about phi? Well, look at this arc length here. In this plane, what can I say about S? The arc length here is equal to R times theta. Right? Now look at this plane. What can I say about ds or S? S is equal to, you see, this plane right here. L times phi. Because S is same thing, so you have this equality. You make these two equal because S is same. So then you get R theta is equal to L phi. This is your second equation. So equation number 1, equation number 2. And what is the third equation? Well, I need to have something for the shear. And the third equation is already here. I just wrote it there. We drew it in the last class. So I had tau is equal to T over J times R. At any section, and because my T is constant, I have T at X. You could say T at X, J at X, right? Because this can change. But for this interval, I assume that this infinitesimal is small, so torque is almost constant, right? So now I have three equations. I want to solve for what? Theta, because I want to find angle of twist. What should I do? Well, first I put phi here in this equation. All you need to do is solve three equations for theta to find theta, right? So at first I substitute 2 into 1. If you put 2 in 1, then you get tau is equal to G times, instead of phi, you put R theta over L. RL over theta. Instead of phi. And then you put number 3. So here then substitute equation number 3 for tau. Tau is equal to T over J times R is equal to G times R over L times theta. Eliminate R, as you can see here, they cancel. Then you get solve for theta. Theta is equal to solve for theta. Then theta is equal to T L over G J. That's it. In fact, they assume that the angle at here is 0 because it's relative to 1. Now, if we had an angle here, already some theta here, like theta is 0, what would be theta here? We just add it to that theta. So in fact, in general, you can write this equation as T is going to be T at any x. Right? L. So L is going to be length of this specimen. Now, if we consider T at any x, that means we consider this length to be infinitesimal thing, such that at that particular x, the length is uniform. Right? So L becomes dx, but this infinitesimal thing, because the length is dx times divided by g at any x times j at any x is equal to delta theta. D theta means the change in the angle when you go from this point to this point. That means if you want to find the total angle of deformation, you have to do what? Integrate both of these. So you do integral from point 1 to point 2, T of x over gx jx dx is equal to theta minus theta 0. Integral d theta from point 1 to 2. So it's theta 2 minus theta 1. That's just simply integral of this relation. Yeah.
Is the angle in radians?
Yes. The angles are in radians. So when you solve this equation, what you get is a gradient. Then you have to convert to degree. So this relation, let me put it here. So you have delta theta. This means delta theta. The relative change in the angle from base to the end is equal to integral from point 1 to 2 dx over gx jx. So this was, I put marker here, equation number 10-14, page 475. Page 475. Although your book uses a different method to write that equation, what I use it on, that is easier to understand and it's more accurate. So now I want to give you example. the angle of twist at point C. Now in your book, you use phi for angle of twist, or use theta. So we have just used different symbols, which is fine. So find the angle of twist at point C. What should I do? Well, I know that I have to use this relation. If I only want to find the torque, I use this relation. But it's not one angle of twist. So I use this relation to find theta. Now, this is the integral between 2 points. What's my first point? Should I take over there? The point on the wall, which is A. And what is theta there? 0. So this is theta 2 minus theta 1, delta theta, right? Theta 2 is what? The angle of twist at point 2. So if I take, this is point 1, so let's say this is point 1, this is point 2. Then theta 2 minus theta 1 is what? Only theta 2, because theta 1 is 0. So then you get theta 2 is equal to that integral. Then what should you do? Let's do it step by step. So I'm using this equation, right? Between point 1 and 2. So you get delta theta, which is equal to theta 2 minus theta 1 is equal to, according to that relation, integral from point 1 to 2, t at any point x, dx divided by g at any point x times j at any point x. That's what I have. And I know immediately, if I choose my point 1 here, point 2 here, what's the angle at point 1? 0. So then, your only unknown is theta 2, which is, that's what I want. This is theta 2, right? So what should I do about this integral? Integral from here to here. Well, I look at the integrand. If the integrand is totally constant, well, I'll just take it out. Can I do that?
No, it's
What about t? Can I take this t out?
you can.
The torque? Yes. You see, if you draw the torque diagram, don't trust it, don't say yes. Draw the torque diagram. That means cut it from here to here, cut it from here to here. Every time you cut it, what's the torque? 20. Right? So yes, this is always 20. So if it's 20, I can take it out. What about j of x? Constant? So you can take it out. So write this as 20, take it out, and divided by j. J is just constant. So what is j? Pi over 2. The radius same is 2 centimeter, the radius. So you have 2, 10 negative 2, 4. That's your j. Take these two out. So finally you have integral from point 1 to 2 dx over g of x. Now that's interesting. We never thought that the shear module of elasticity is variable. Well, there is a course called composite material. And then in that course, your Young module of elasticity is different. Your shear module of elasticity is different in different location in your material. Right? Then you have to do this kind of thing. You cannot just take, if everything was constant, what do you do if everything is constant? just take this and this all out, so it's going to be integral, if everything was constant, it's going to be integral from point 1 to 2, right? T, Gj, dx. And what can I write about this when x is equal to 0 to, x is equal to L, the entire length. Then, what is the end result? TL over Gj. That's exactly the formula we write. But I don't have this case. In this case, my G is variable, right? So what can I do about that? Do I have a function G of x so I can put it there and take integral? Well, the thing that you're trying to get is expand the integral. Instead of saying integral from here to here, let's say integral from here to here plus integral from here to here. Again, back to the calculus, we had integral from a to b is equal to integral from a to c plus integral c to b. If c is between a and b. We mathematically proved it, and then you say, I don't like proof, but that's because you need it here. In fact, mechanical engineering is very mathematical for civil. So here, I just expand the integral from point 1 to 2. I expand it from point A to B, and then from B to C. So I write that integral equal to integral A to B 1 over G dx plus integral B to C 1 over G, and this is x dx. That's exactly the same integral, right? So what's the result of this integral? Well, here, from A to B, what is my G?
Constant.
The constant. So take it out. So it's going to be 1 over G from A to B, which is 1 times integral A to B dx. Sum of the length from A to B, which is what? 1, which is L A to B, which is 1. So 1, so you get 1 over G1 plus 1 over G2. You see that? In general, this is LAB, LBC. So now put it here. Then you get 20 divided by pi over 2. 2 10 to the negative 2, 4, 1 over G1 plus 1 over G2. There you are. That's point. There are point C. In radian. That's in radian. Now here comes the final derivation. And we have a very limited time. And when it comes to final derivative, it doesn't write. So the question is find the reaction and work. And you solve it. What kind of problem? Say this is final paper. That means if you solve it, you don't do final exam.
Do I have to go up there to solve it?
Yes, yes, that's right. And it's only one opening, one opportunity. G of the steel is equal to shear energy of the steel. Okay. GPA. So we have all material properties. We have two materials welded together. The length, diameter, the property, everything. They're fixed between two walls. And now we apply torque in the middle of it. Now find the external reaction. How many external reactions do I have? This is a three-dimensional object. So at any point, you have 6. At any point here, you have 6. But look, do I have force in this direction? No, right? Do I have force in this direction? Well, they don't cancel out. They cancel out. You see, it's this way and this. So no force in X, no force in Y, no force in Z. What about torque? You're gonna have a torque only this way. You see this, the axial torque, right? The one that causes torsion. Do I have torque in other directions? Bending torque, no, right? So how many equations do I have here? For this object, for the dot object, how many equations do I have from vector statics? Just one, right? The rest is null. 0 is equal to 0, because I don't have anything in other direction. So how many unknowns do I have? Huh? You have one unknown torque here in this point, one unknown torque here, this point. So how many unknowns do you have? 2. How many equations do I have from vector statics? Just one. So can I solve it just using vector statics? No. So that's the reason this problem called statically indeterminate. Now we have to add one more equation. How can I add one more equation? Mechanics of material. And mechanics of material, deformation. You see, the deformation analysis you do is only used to make everything determinate. And what is that deformation equation? Don't expand it, just express it, just write it. I'm not asking you the detail of that equation. What is that equation? Physically. Huh? What? What's the equation that I need to add to my moment equation in order to make it determinate? Because I have 2 unknowns, 1 equation. if I take a point here, and when I apply this torque, you see this is a counter moment. You see everything will rotate this way. But what about point here with respect to point here? Rotation of this point with respect to point, rotation of point here. What happens to rotation of this point with respect to rotation of this point? No rotation. You see they're fixed to the wall. So this point here will not rotate with respect to the point here. What about this point with respect to the point in the middle? Well, with respect to the point in the middle, because when you apply this torque, this point is going to rotate like that. So this relative to that has some information. If somebody sits here and look at the point here, you see some rotation, angle of twist. But if somebody sits here and look at the person here, from the beginning to end, he sees no deformation, no rotation. So the relative rotation of this point with respect to this is what? That means delta theta from here to here is equal to 0. That's the second equation. So the first equation is summation of moment is 0. The second equation is relative angle of twist is 0. So you have two equations, two unknowns. Right? Thank you. I accept it. That's right. You see what he did? I'm just so happy that some students, they really practice at home. I accept it. Thank you. Please email me if you want to see it. So you see we have students like him, and he always try to catch up with the class, come to the whiteboard, do all the, you know, even if he fails, he just tries to contribute. And most of the time, he was successful. And again, we have a student like him, he gets bonuses, and then we still have some students, they don't practice at home, and the result, they get lost in the class. And then, when it comes to the final midterm, they don't say anything, but the final week of the classes, they come to my office and say, well, can I have another opportunity? Give me extra projects. I mean, what is that? Yeah.
Shouldn't they be added together?
No.
They're supposed to be subtracted?
Why? Because when we expand it, we are going to do that hopefully next class. We are going to do that next class in detail. So if you expand that, then you see T from here to here times the length from here to here, which is 1. Divided by G, which we have it, times J, which we, that's exactly what we did.
Yeah.
But T from here to here is going to, if you draw the shear, the torsion diagram, you see the torque here is going to be negative. It's going to be the opposite. You will see that. We'll do that next class. So, again, what I'm saying here is this is not the kind of course that I can go over all examples in the book, because the class time is very limited. So when you go home, don't wait on me. Don't wait on the homework. You see, we have homework for this week. But that doesn't mean anything at all. Just don't wait on me. Go ahead, solve all the problems in the book. Your assignment, they say give us some assignment. Well, your assignment is to solve every single problem in this book. Every single problem in this book. Now, how can you find the solution? Most of them, the solution are given in the appendix. I mean, you know that. I think you know that, right? You know that. And some of them are not available in this book, but you can find it on YouTube. The way you actually answer the question when I put homework, you see everybody is perfect. So you need to find the solution manual for that. Where is that? Available online. So all you need to do, When you read the question, close the book, close your browser, think about it. 20 minutes, 1 hour, 2 hours, 3 hours. It's gonna be a lot of time. You're gonna waste a lot of time, but finally you learn. That's the way he does. And the students like him, he's not gonna be person in his class. So,